Welcome back. So last time we went through kind of a whole bunch of math, but it was on looking at inviscid and potential flow theory, but with a finite airfoil. And we were able to work through a lot of the math. We looked at the downwash, sidewash, and we were able to get relations for lift and drag. And in fact, what popped out was how the drag has the penalty, the kind of the lift penalty associated with it. So that's pretty neat what you can get even from just kind of finite theory. And so I want to finish with a couple more. Now, since Kuchemann doesn't necessarily derive these ones either, I didn't, but you can go derive some of this, because some of it just implies you have to have the right form of the potential. But the first one we'll talk about is, again, if you have an airfoil and then you have some flow coming at it at some angle, right? So this one actually might, let's say, if you have flow kind of going around, and remember we talked through the cut condition where certain pieces have to come off, so it's even, right? So here's your flow. Good enough. Well, the interesting thing is, even with this solving for the potential flow, you can actually walk back here, and if you notice, I'll try to circle in red, and I know this is just me sketching, but the angle of attack right there is a little more, or a little different than you would have. Okay, and so it's basically that incident angle. You can actually go back and show that it's that Ch3 velocity over v0. So it's actually the downwash. the angle is the downwash angle, and that's the incident angle you get. And so that, which is just, I'll just write it down. That's 1/2. Again, that downwash, V0, and then lift over pi aspect ratio. And so with this, you can actually see it's an effective angle, which is alpha minus that 1 over pi a lift. And so we see this, anyway, the point is we see this in fluid mechanics, absolutely, and potential flow also gave us this. That was pretty neat. Okay. The other thing that the potential flow can give us is the chord-wise loading, right? This is the chord, like along the direction of the flow. How is the pressure loaded, right? Because we solve for the potential flow means we can go back and solve again for the pressure all over for it. And so the loading as a function of x, right, along the streamline of the chord is just, again, by definition would be that the change in pressure normalized by the dynamic pressure, and that is 4 times the effective, again, effective, not actual angle of attack, and then square root of the trailing edge minus x minus the leading edge, L. So it's got a final form. Again, the book didn't derive it, so you're welcome to go take a look at that. But again, some of this comes from the solved analytical forms. And then this is where we can actually go and see how the loading's got sort of that maximal point. And then you can actually integrate this and show that the center of pressure indeed is at the quarter chord. Once you're supersonic, it goes to the mid chord. Okay, and so that's pretty sweet. And then you can also go and show how it's elliptic. That the maximum, the minimum drag condition would be when this is elliptic. Okay, and so CL would be 8 times the span over pi a, and then square root of 1 minus y over s. Okay, so some pretty cool things from this, and I'll now just zoom out and kind of write the big couple ones from this. Okay, the first one is that we kind of already, you might have already heard this one before, but if we want to maximize this, so if we want to do that, then we already know the aspect ratio should be as big as possible. We know that. So the most efficient wing is the really long wing that takes a whole bunch of sort of inflowing area and only does a slight downwash to it, right? That's what we want. Now, however, this is going to be counter, I'll just put bad for structure, right? This isn't going to be what you want to do from a structure point of view over from a mass fraction point of view. So we know there's at least going to be balance. This is going to drive the efficiency up, but there's some balance based on your materials and other configurations that you would need to go do at the system level. Okay. The second one is just there's a generalization that we're going to say the drag is going to pick up. We'll go ahead and keep this pi and aspect ratio, but we normally just then say some kV, this will be drag factor, and then CL squared. So we will stick to that notation since we know that for KL of 1, this is true for inviscid. Any other deviation from it, we'll actually be able to kind of put in that. Okay, another really interesting one is that even from this, you can show, let's say I had an aircraft looking on and you had really long wings, you can actually show the effect of putting end plates on the wings, right? So you've probably seen some planes with the winglets, and we know it actually reduces drag. Okay, what it actually doing is kind of preventing, you can think of it as preventing the vortex from shedding quite so ferociously. So it's a drag reduction technique. Even at my old company, Exoscent, we put those on the trailer just to kind of cut that vortex. It's pretty sweet. But the interesting thing, when you walk through the math, I won't walk through the math here, but what I'll just say is this is equivalent to if I had this, and I should have done a different color, but it's equivalent to just doing that. The drag reduction is whatever this length is. If you had just made a longer wing, it would have been the same. And you can walk through that analytically. So really what that's showing is don't do the end plates unless you have another reason to do the end plates. Well, one of the reasons you could do the end plates is maybe these are towards the back of the aircraft and they actually serve as a little bit of a vertical stabilizer. So you can imagine even like a delta-shaped vehicle if you wanted, where you had end plate winglets, and it would actually be useful, right? Kind of doing double duty. It's not just extending, but it's also providing some stabilization. So that's pretty cool. Okay, and we can show that again just from inviscid potential flow theory, doing all this math. And then since I drew this, the last thing that there is a non-planar vortex lift that we'll get to certainly in other chapters, is that this thing can generate a vortex lift, which will then drive more lift out of these lifting bodies. And so you can actually still kind of show that with the potential theory. So pretty useful. So far, in chapter 3, we kind of went through a whole bunch of math. We stuck to inviscid potential theory, got a bunch of relations, got the fact that we were able to show the drag goes like lift squared. We also kind of understood how, really this is a little about downwash, and we knew that large aspect ratios going to infinity actually drives LVD max the most. And then really interesting thing here with the end plates, we can show that it's effective, but make sure it's doing double duty. So next time we're going to get into more on the propulsion side of things and kind of wrapping up all of chapter 3. Next time we're getting into supersonic, and then we'll get into propulsion. Okay, so we'll see you next time for supersonic.